born about 1,000 years ago in what is now Iraq. Alhazen ibn al-Haytham, known in the West by the Latinized form of his first name. Originally Alhazen and later Alhazen, was a pioneering scientific thinker who made significant contributions to the understanding of vision, optics, and light. His methodologies of inquiry, particularly the use of experiments to verify theories, bear some resemblance to what has come to be known as the modern scientific method. Through his Book of Optics, Kitab al-Manazir, and its Latin translation, De Aspectibus, his ideas influenced European scholars, including those of the European Renaissance. Today, many consider him a seminal figure in the history of optics and the father of modern optics. Ibn al-Haytham was born during a creative period known as the Golden Age of Muslim civilization that saw many astonishing advances in science, technology, and medicine. In a region stretching from Spain to China, inspiring men and women from many religions and cultures, built on the knowledge of ancient civilizations, making discoveries that had a profound and often unappreciated impact on our world. Ibn al-Haytham, the pioneering scientist, Ibn al-Haytham's work is notable for its emphasis on evidence and proof. He is known to have said, "If the pursuit of truth is the aim of the scientist, then he must make himself the enemy of everything he reads." By this, he meant that it was important to carry out experiments to test what was written, rather than to accept it as truth. Ibn al-Haytham was born in 965 in Basra and died around 1040 in Cairo. He was one of the first scientists to study the characteristics of light and the processes of vision. He sought experimental evidence for his theories and ideas. During his years in Egypt, 10 of which were spent under what we now call protective custody, house arrest, he wrote one of his most famous works, Kitab al-Manazir, whose title is commonly translated into English as Book of Optics, but more accurately means Book of Vision. Ibn al-Haytham made significant advances in optics, mathematics, and astronomy. His work on optics is characterized by a strong emphasis on carefully designed experiments to test theories and hypotheses. In doing so, he followed procedures somewhat similar to those followed by modern scientists in their vision could be explained have circulated for centuries, especially among classical Greek thinkers. Some said that rays of light emerged from the eye, while others thought that something entered the eye to represent an object. However, it was the 11th century scientist Ibn al-Haytham who systematically criticized these ideas about vision to show through reason and experiment that light was an essential and independent part of the visual process. Thus, he concluded that vision would only occur when light rays either emerged from a luminous source or were reflected from that source before entering the eye. Ibn al-Haytham is credited with explaining the nature of light and vision through his use of a dark chamber he called the albiyat al-Muslim, which in Latin is called the camera obscura, a device that became the basis for photography. Of the 96 books he is recorded to have written, only 55 are known to have survived. Books related to the subject of light include The Light of the Moon, The Light of the Stars, The Rainbow and the Halo, Spherical Burning Mirrors, Parabolic Burning Mirrors, The Burning Sphere, The Shape of the Eclipse, The Formation of Shadows, Discourse on Light, and also his masterpiece, the Book of Optics. Latin translations of some of his works are known to have influenced important thinkers of the European Middle Ages and Renaissance, such as Roger Bacon, René Descartes, and Christian Huygens, who knew him as Alhazen. The crater Alhazen on the Moon is named in his honor, as is the asteroid 59239, Alhazen. Born in 965 in Basra during the intellectual heyday of Muslim civilization, invited to Egypt to help build a dam on the Nile River. After a field trip, he refused to continue the project, which led to him being placed in what we now call protective custody for 10 years. From his observations of light entering a dark room, he made major breakthroughs in understanding light and vision. His discoveries led him to make significant revisions to the ancient view of how our eyes see. Through his study of the earlier work of Galen and others, he gave names to the parts of the eye, such as the lens, retina, and cornea. He set new standards in experimental science and completed his great book of optics around 1027. He died at the age of 74 around 1040. His book of optics was translated into Latin and had a significant influence on many scientists in the Middle Ages, Renaissance, and Enlightenment. For example, the book of optics Perspectiva was written around 1275 by Erasmus Wheatelo, who was later nicknamed Alhazen's ape when people realized that he had copied most of Alhazen after centuries of intense activity in mathematics, astronomy, optics, and other physical sciences. Although he was preceded by great pioneers such as Aristotle, Euclid, Ptolemy, Al-Kindi, Banu Musa, Tabit ibn Qura, Ibrahim ibn Sinan, Al-Kuhi, and Ibn Sal, his work was very recent. The world of Ibn Haytham. Ibn al-Haytham stands out in this long list as a leading figure in the science of light and vision because his work relied heavily on experimental demonstrations. His work is important for two reasons. 1. Ibn al-Haytham showed that one sees an object through something that enters the eye, and not something that comes out of the eye. Before Ibn al-Haytham, both of these ideas had been put forward by other scientists and scholars who wrote in Greek, Latin, Arabic, and other languages. 2. Ibn al-Haytham used systematic experiments in his work on optics. Ptolemy, who worked in the Greek culture of Alexandria in the 2nd century, had used a similar approach in his work on optics. However, Ibn al-Haytham's work was relatively new. Ibn al-Haytham benefited greatly from being able to use the works of previous generations of scholars that had been translated into Arabic over 200 to 300 years under the patronage of various Muslim rulers and wealthy nobles. This included direct translations of many scientific works from Greek, Syriac, and Persian that were heirs to the great scientific traditions of ancient Egypt, Babylon, India, and China. In turn, Ibn al-Haytham's work proved equally influential on scholars writing in Latin during the Middle Ages and the Renaissance. In this way, he became part of the intellectual legacy that Latin scholars acquired from Muslim civilization from the 13th century onward, including the Renaissance and early modern periods. With new scientific insights such as those of Ibn al-Haytham, as well as medical miracles, astronomical observations, new maps, libraries, and sophisticated schools teaching a variety of mathematical subjects, Muslim civilization made significant and crucial contributions to the accumulation of scientific knowledge in the pre-modern era that transformed the ancient world. These past discoveries have shaped our homes, schools, hospitals, cities, the way we trade, travel, and our understanding of Ibn al-Haytham's life. The story of Ibn al-Haytham's life and discoveries is truly remarkable. Born in 965 in Basra, he made significant contributions to our understanding of vision and light, bringing important new insights into both subjects. However, his brilliant breakthroughs came at the darkest time in his life. Ibn al-Haytham grew up in a time when schools and libraries were thriving in Muslim civilization. Students had access to highly trained scholars who could teach a variety of subjects, including law, literature, medicine, mathematics, geography, history, and the arts. Debates and discourses were popular and took place in Arabic. Scholars enjoyed discussing ideas from newly translated ancient manuscripts. Ibn al-Haytham's scholarly reputation spread far beyond Basra. He is known to have said, "Confidently, if I were given the opportunity, I would implement a solution to regulate the flooding of the Nile." This claim reached al-Hakim, the Fatimid Caliph of Egypt, who invited him to Cairo. Confident in his own abilities, Ibn al-Haytham boasted that he would tame the mighty Nile by building dams and reservoirs. But when he saw the enormity of the challenge and the astonishing remains of ancient Egypt on the banks of the river, he reconsidered his own boastful thinking. If such a grand project could be done, he reasoned, it would have been done by the brilliant builders of the past, who had left us such fantastic architectural treasures. He returned to Cairo to inform the Caliph that his solution was impossible. Knowing that the Caliph would not allow failure and that his life would be in danger if he failed, Ibn al-Haytham feigned insanity to escape the Caliph's wrath. He knew that Islamic law would protect a madman from responsibility for his failure. Despite the caliph's mood swings, he remained steadfast in his adherence to Islamic law. Rather than executing or banishing Ibn al-Haytham from Cairo, the caliph decided to place the scholar under permanent protection. This was required by law to ensure his safety and that of others. Ibn al-Haytham was placed under house arrest, away from the lively discourse and debates he was accustomed to. Ibn al-Haytham made perhaps the most remarkable discovery he is remembered for. Legend has it that one day he saw a light shining through a small pinhole into his dark room, projecting an image of the outside world onto the far wall. Ibn al-Haytham realized that he was seeing images of objects outside that were illuminated by the sun. From repeated experiments, he concluded that light rays travel in straight lines, and that vision occurs when these rays enter our eyes. Ibn al-Haytham confirmed his findings through experiments in his dark room, which he called al-Bayt al-Muslim, which in Latin is called camera obscura, which simply means dark room. After many additional experiments using special equipment, such as lenses and mirrors that he had made, he outlined his new ideas about light and vision in the 7-volume Book of Optics. He was released from prison after the caliph's death. Ibn al-Haytham died at the age of 74 in 1040. His greatest work, the Book of Optics, may have been begun in prison and completed around 1027, but its impact was worldwide. Both his optical discoveries and the fact that they had been validated by direct experimentation would influence those who followed him for centuries. So how did that influence shine on later generations? In the early 12th century, Toledo in Spain was the focus of a major effort to translate Arabic books into Latin. Christian, Jewish, and Muslim scholars flocked to the city, where they lived side by side and collaborated to translate ancient knowledge into Latin and then into other European languages. Ibn al-Haytham's Book of Optics and several other scientific works were translated into Latin and made available to European scientists, including Roger Bacon, Johannes Kepler, and even Leonardo da Vinci. How Ibn al-Haytham changed the course of science. Ibn al-Haytham's discoveries in optics and vision overturned centuries of misconceptions. In his experiments, he observed that light entering through a small hole traveled in a straight line and projected an image onto the opposite wall. However, he realized that light entering the eye was only the first step in seeing. He built on the work of the Greek physician Galen, who had provided a detailed description of the eye and the optic pathway. Today, the oldest known drawing of the nervous system comes from Ibn al-Haytham's Book of Optics, which depicts the eye and optic nerve. Ibn al-Haytham proposed that only light rays that strike the surface of the eye directly will enter the eye, thus creating an image of the world. Kepler in the 16th century corrected this and proposed that the object of vision, what is seen, comes from perpendicular rays and angular rays that strike the eye to form an inverted image. Other insights was his understanding of the important role of visual contrast. For example, he realized that the color of an object depends on the color of its surroundings, and that contrasts in brightness explain why we cannot see the stars during the day. Ibn al-Haytham also adopted a method of empirical analysis to accompany his theoretical postulates, which in some ways resembles the scientific method we know today. He recognized that the senses were prone to error, and he devised a method of verification, testing, and experimentation to uncover the truth of the natural phenomena he perceived. Up until this point, the study of physical phenomena had been an abstract activity with occasional experiments. In his search for evidence, Ibn al-Haytham studied lenses, experimenting with various mirrors: flat, spherical, parabolic, cylindrical, concave, and convex. The results of his experiments were clear. The visual objects we see through the refraction of light, through thick materials such as water and glass, are larger than their actual size, he wrote. After his death, Ibn al-Haytham's writings were more influential in Latin than in Arabic. The only significant work in Arabic that built on Ibn al-Haytham's ideas was produced in the early 14th century, in present-day Iran, by Kamal al-Din al-Farisi, who was also a brilliant scientific thinker. When Ibn al-Haytham's Book of Optics was translated into Latin, it was very influential and widely read. It was published in a printed edition in 1572, making it more readily available. The Polish astronomer Johannes Hevelius chose to honor Ibn al-Haytham, along with Galileo, in his most famous work on the moon, Selenographia, published in 1647. Some of the questions posed by Ibn al-Haytham remained unsolved for 1,000 years. One of these was called Alhazen's problem, to which he offered a geometric solution. Given a light source and a spherical mirror, find the point on the mirror from which the light will be reflected to the eye of the observer. Ibn al-Haytham solved this problem geometrically, but it remained unsolved using algebraic methods until it was finally solved in 1997 by Oxford mathematician Peter M. Newman. However, some mysteries remain. Ibn al-Haytham claimed that an optical illusion was the reason why the moon appeared so large when low in the sky near the horizon compared to its size when at its zenith. However, no one knows why this is so. This, and other questions in science, remain unsolved. This leaves us with an interesting legacy to consider today.